Week is a new functional group. We're going to start talking about aldehydes and ketones. All right, so these are our first carbonyl containing functional groups. All right, an aldehyde is a terminal carbonyl located at the end of a molecule. And a ketone is an internal carbonyl. So now that carbonyl group is located in the middle of the molecule. All right, and we lump these two functional groups together. They have very similar properties, very similar reactions, so that's why we're going to combine them together in this chapter here. All right, we're going to talk about physical properties. What do we think this functional group, polar or nonpolar? Polar. We got a polar bond here, right? Our oxygen is able to pull electron density onto itself away from that carbonyl carbon. So we definitely have a polar bond here. All right. And so acetone is one of ketones and aldehydes are one of our polar functional groups. We were talking about the strength of intermolecular interactions of our previous functional groups from this unit. So where does our aldehydes and ketones fit into this? Again, we want to pick something that's a similar size. So we're going to do 2 carbons and an oxygen, right? But an aldehyde rather than an alcohol. All right, this molecule right here has a boiling point of around 20 degrees Celsius. All right, so not quite as strong as that much larger polarizable sulfur atom, but still compared to our ether has a much larger dipole-dipole interaction. All right, so here is our, in this case it's an aldehyde. Whereas ethers, we said they have a very weak dipole-dipole interaction. We're going to make note that our aldehydes and ketones, our carbonyls, have a strong dipole-dipole interaction. As you all know, we use acetone to clean our glassware in the lab. That's because it kind of sits in the middle of that polarity spectrum. It's soluble with water, it mixes with water, but it also will dissolve all of that non-polar organic crap that's on our glassware. Okay, so let's kind of introduce now to reactions of aldehydes and ketones. All right. These two functional groups, it's always bothered me a little bit that they're considered two different functional groups because their behavior is very similar, right? They're both carbonyl-containing compounds. Why did we divide these up into two different functional groups instead of saying something like a terminal carbonyl or an internal carbonyl, right? We have primary, secondary, tertiary alcohols. Why didn't we just do a similar thing with these two? Instead, they're divided into these two separate camps. So why is that, okay? So it's really historical reasons. If we knew what we knew now, then we probably would lump them together, all right? But back in the day when organic chemistry was starting, when these functional groups were starting, they didn't have NMR. They really didn't know what these bonds looked like yet, right? So the way that they were dividing the world up was just based on what reactions molecules had. These molecules undergo similar types of reactions, we're going to put them into this bucket. These molecules undergo this type of reaction, we're going to put them in this bucket. And that's why aldehydes and ketones got separated, because they share most reactions except what turned out to be a pretty big one, oxidation. So because these two functional groups oxidize differently, they were put into two separate buckets. All right, so everybody's going to take a second and remind themselves, if we take our aldehyde here and we hit it with an oxidation agent, what are we going to get? Compared with if we just took this exact same number of carbons and oxygens, but we moved that carbonyl group to the middle of the molecule, boom, what reaction will we get? All right, everybody take a second, complete these chemical equations for me. All right, what do aldehydes oxidize to? What's my functional group? Carboxylic acid. Remember, oxidation is taking carbon-hydrogen bonds. I guess I should note there's an implied hydrogen here for an aldehyde, right? Replacing carbon-hydrogen bonds with carbon-oxygen bonds. That's what oxidation is. Boom. And what about a ketone? What does a ketone oxidize to? Can't happen. All right? This carbon has no carbon-hydrogen bonds anymore. It can't be oxidized anymore. Okay? So, like I said, aldehydes and ketones, they share most reactions. Every other reaction that we're going to talk about here, aldehydes and ketones both have, except this important one here, which is why they were lumped into these two different camps. All right? That's why there's two separate functional groups. It also has a lot to do with like early biochemistry stuff as well. It turns out that sugars are either aldehydes or ketones. So there's all this work going on with sugars that also help to reinforce these two separate camps. Some of those sugars were oxidizable because they were aldehyde sugars. Other ones were non-oxidizable because they were ketone sugars. Cool. All right. So then what are all these other reactions that they do share? Okay, 90% of the reactions that we're going to study for aldehydes and ketones fall into this bucket of being nucleophilic addition reactions. All right, so first of all, let's draw a ketone. We're going to note actually explicitly that these reactions are shared by both aldehydes and ketones. So even though I'm doing an example with a ketone here, we could also use an aldehyde. All right, and our aldehyde and ketone in our chemical reactions, what role are they going to play? The nucleophile or the electrophile? Electrophile, where? That carbonyl carbon. All right, look, so this phrase has to be just ingrained in your mind here. We have this electrophilic carbonyl carbon. I want you to chant it to yourself before you go to bed at night. Make sure we remember it. All right, and maybe you know that because I told you to spy these patterns. I told you that carbonyl carbons play the role of an electrophile. You were like trained to sort of spot that. But why? Why is a carbonyl carbon a good electrophile? So oxygen pulls away electron density. So step one, right? Remember, in order to be a good electrophile, you have to be electron poor. And it's electron poor because it's in this polar bond with oxygen. All right, so if we looked at our electron density here, we would see that this carbon has very little electron density because this oxygen is pulling all that electron density onto itself. All right, so step one, we have this electron poor carbon. All right, but that's not all you need to be an electrophile. Because if we think about it, alcohols, we said, are not electrophiles, even though that's a polar bond. That's another carbon-oxygen bond. So what makes this a good electrophile, but alcohols bad electrophiles? Why were alcohols bad electrophiles? Because they have bad leaving groups, right? So here, importantly, another criteria for a good electrophile is it has to be able to accept a pair of electrons. That's why alcohols were bad. They had a polar bond, but they couldn't accept electrons because they couldn't kick off a leaving group. So why is this, if I take some nucleophile, why is this able to attack this carbonyl carbon? Because what's going to happen at the same time? That pi bond, right? So we have this built-in pi bond leaving group. We're going to put leaving group in parentheses here because it's not quite a leaving group, but it plays that same function of making it so that this carbon can accept electrons and notably without ever breaking its octet, right? So that's nice because carbon would hate to break its octet. So this it can accept electrons and then it just bumps that pair up onto that oxygen. Carbon never broke its octet. All right, but there's another reason, yet one more reason why this is a nice electrophile. And this had a lot to do with what we were talking about last week. Remember, with all these epoxide reactions, with our Williamson ether synthesis, we were always looking for our electrophile to be more what? Like what made a primary so much better than a tertiary? The accessibility, right? And this is a nice accessible carbon. And why is that? Simply because of the geometry. This is an sp2 hybridized carbon, which means that this is this trigonal planar geometry. So in a molecule, let's say that you have a big, long molecule. Once you get to that carbonyl group, the molecule's flat at that particular region. So it's just really easily accessible to get to your carbonyl carbon, all right? So accessible because it's got that trigonal planar geometry. All right, so carbonyls are good electrophiles. They check all the boxes. They're electron poor, they can accept pairs of electrons, and they're nice and easily accessible. All right. We spent a lot of time last week, and we're going to do so again, about talking about these different conditions for our reaction mechanisms. All right, so we're first going to look at what's generally the easier of the two. That is our basic conditions mechanism. All right, and remember what we said to be under basic conditions, we should have no positively charged intermediates. All right. So let's take our ketone here. Just going to do acetone as our example, but again, these are reactions shared by both aldehydes and ketones. And I'm going to react this under basic conditions, so let's just choose that quintessential base, hydroxide. What's going to happen? What's going to be my nucleophile? What's going to be my electrophile? So hydroxide is my nucleophile. My ketone then is my electrophile. What's my electrophilic site? That carbonyl carbon. What's my nucleophilic site? That oxygen that has that negative charge, right? So what did nucleophiles do to electrophiles? They attack. All right, and again, we're going to attack that carbonyl carbon, and then in the same step, again, why it's so good at accepting pairs of electrons is because it's got that built-in pi bond leaving group. Okay, we're going to be good. This is a reversible step here. Okay, my intermediate. Have an OH and an alkoxide all in the same place. Is this intermediate allowed under basic conditions? Yeah, I'm allowed to have negatively charged strong base intermediates because we're under basic conditions. All right, so then now let's say that I tell you that the next step, or rather I'm going to tell you that the product of the next step has these two alcohol groups on that same carbon. We're going to need something to donate a proton. We can't have any strong acids, but we can have a weak acid like water. Exactly. All right, so we're going to protonate that oxygen, creating what we call a Chem diol. Gem, I'm pretty sure, is a prefix for twin or something like that, right? Gemini? I don't know. I don't know where it comes from. Anyway, twin diols, right? Two alcohol groups on the same carbon. All right, so these Chem diol formation reactions are important. They occur all the time. You can prove that by watching oxygen get exchanged with your solvent. But importantly, this equilibrium does strongly favor our reactants. All right, so we have very little product that's going to be formed in this equilibrium, but nonetheless, it's bouncing back and forth and back and forth and back and forth all the time. All right, we can do this same reaction here, but under acidic conditions. All right, what am I not allowed to have under acidic conditions? We said under basic conditions, no positively charged intermediates. What is it going to be for for acidic conditions? No negatively charged intermediates. All right, so I'm going to take that same acetone. All right, but we're in now acidic conditions, so I'm going to put hydronium in there. All right, but I also need that neutral water nucleophile here. Okay, and I want everybody to try to predict our mechanism to get to that same Chem diol. All right, this is where we're going. So take stock of what bonds we need to make, what bonds we need to break, and then I want you to try to fill in the steps of this mechanism. I will tell you that there are 2 missing intermediates here. All right, so give it a shot. And as I said before last week, you know, when you're doing these mechanisms, you can't be afraid to make a mistake. Some people look at it and they say, I don't know what to do next, right? And then they just stop there. Try something. Try pushing some electrons around, right? See what your result is. See if that makes sense in the given conditions. But just go for it, all right? Oh, whoops. Missing one arrow. This isn't, your acids play the role of what? Electrophiles. You have that first step correct. You're on the right track. You're on the right track. slightly better way. All right, but I like this. I mean, this is perfectly logical. You didn't break any rules. Everything is good here, but I'm going to show you a slightly better way. So, yes, okay. You're on the right track here, but why? Where's your pi bond? Yeah, it looks like you have it. So put in arrows. Put in the arrows on the first step, and let's follow. Okay, is that the direction that the arrows are going to flow in a bond? You can try it both ways, or just try it out. I will say that that is a perfectly legal way to do it in terms of electron pushing arrows.
Okay, but all in that first step, that can happen
It doesn't actually. I'll show you a better way. But if you did it in that now as a way, I'd be very proud because that is a legit sort of mechanism that would get you from A to B and follow all the correct rules.
Okay.
But I'm going to show a slightly better way. Awesome. Missing one charge here, but you're there. Okay, so let me show you what's going to happen here. In our basic mechanism, we did nucleophilic attack first, but if you did that this time, you would see that that wouldn't work because you would get that negatively charged intermediate. So the first thing we're going to have to do is protonate our ketone. My acid's going to be my electrophile. My oxygen's going to be my nucleophile. All right, once we have our protonated ketone, importantly, under acidic conditions, because you get this protonated ketone here, you're allowed to use these weaker nucleophiles, like neutral water, because that makes this an even better electrophile. Now that oxygen, because of its positive charge, is pulling even harder on that pair of electrons up onto itself. So this makes it perfect for water to attack, and that pair of electrons get bumped up onto that oxygen. All right, then we have one more step to go here, because since water joined, now that oxygen has 3 bonds and 1 lone pair. So we're almost there, but not quite. We need to protonate, or rather deprotonate this oxygen here. All right, and so we need a base. We can't use our strong base, so what are we going to use? Water. Boom, boom. So that's how we get from A to B on that one, or A to B to C to D on that one. All right. Importantly, just like our other conditions here, this is an equilibrium that very strongly favors that aldehyde or ketone. Okay. Now, let me just say, a lot of people did a very similar mechanism. Whoops. Copy this. All right, but instead they had either in the first step or in a separate step, they had this pi bond breaking and coming up here onto this oxygen, which meant that their intermediate didn't have a positive charge on the oxygen, but rather this was neutral and we had this carbocation intermediate. A lot of people had this instead. And I'm super proud. If you got there by going through this route here, you followed all of our rules for electron pushing arrows, you don't have any negatively charged intermediates, this is a fantastic guess here. But this way that I did is better. All right, so let's think of why that is for a second. What we're gonna do is we're gonna compare these two intermediates side by side. So I'm gonna take this one here, where the positive charge is on the oxygen. And I'm gonna compare it to this one here, where the positive charge is on the carbon. And I'm telling you that the one on the left here is better than the one on the right. Why is that? More stable, so it is, for sure. This is more preferable because it's more stable. But those are kind of saying the same thing in the energy world, in the chemistry world, right? Something that's more stable is always more favorable. So why is it more stable? What is it about the positive charge on the oxygen that's better than the positive charge on the carbon? So oxygen is actually more electronegative than carbon. So you would think that the more electronegative atom would not want the positive charge, right? But it is. It's more stable here than it is here. So why is that? Carbocations were different from all the other formal charges of +1 or -1 in that how many electrons does this carbon have in its octet? 6, all right? So carbons are weird. When they form positive charges, they have to break their octet. How many electrons does oxygen have in its octet here? 8. It doesn't have its octet broken, right? So this is more stable because we have no octet rule violations. All right, that's not to say that we don't see carbocation intermediates. It's just it won't form here because it can more stably form on that oxygen. So what we're going to see over and over and over again in these reactions of aldehydes and ketones is nucleophilic attack and that pair of electrons jumping up onto the oxygen. These always happen in the same step. They're not broken up into different steps where you would get that carbocation intermediate. All right, so you always do these together. We're going to see this over and over and over again. Cool. All right, so we talked about basic conditions, acidic conditions. Now let's just look at a bunch of different nucleophiles that we can use. Aldehyde and ketone nucleophiles. All right, our previous chapter we talked about epoxides. Epoxides react with anything. They're just so unhappy being in that little ring, they react with anything. Aldehydes and ketones react with a lot of our nucleophiles, but it is a slightly smaller list here. All right, so what we're going to see are the same atoms playing the role of the nucleophile. So we're going to break it up by this nucleophilic sites. We have oxygen, sulfur, carbon, and hydrogen. What element am I missing from this list here that we usually talk about with regard to nucleophiles alongside oxygen? Nitrogen. And I'm going to put nitrogen last on this little chart here because we're going to see nitrogen's a bit of an oddball in how it reacts with aldehydes and ketones. All right. And what we're going to do is we're going to sort of break these up into these different categories. We're going to talk about which nucleophiles work under acidic conditions. I'm going to highlight those in red. And which nucleophiles work in basic conditions, and I'm going to highlight those in blue. Okay, so oxygen, our oxygen nucleophiles would be something like water or an alcohol. Or we could have hydroxide or an alkoxide, a deprotonated alcohol. All right, out of my different oxygen nucleophiles, which one of these are acidic condition nucleophiles and which one are basic condition nucleophiles? These ones you said were basic. How do we tell? That negative charge. So these ones I'm going to put in blue. These are my basic ones. And what about my oxygen nucleophiles? What about the other two, water and the alcohol? Acidic conditions, and what gives it away? The neutral. All right, so if you were given an alcohol and told what reaction does it have with an aldehyde or ketone, you would know that you had to have it under acidic conditions because it's neutral. If you were given an alkoxide ion, you would know that you would be talking about basic conditions because it's got that negative charge. All right, we could play the same game with sulfur, dihydrogen sulfide, or a thiol, or we could deprotonate it. That hydrogen sulfide ion, or that alk sulfide ion. All right, which one of these are going to be acidic? The neutral ones. And which one of these are going to be basic? The negatively charged ones. Okay. So we also talked about carbon nucleophiles. Carbon you don't usually see as a negatively charged atom, negatively charged ion. There are some exceptions when it's stabilized by some high order bond. So one that we see a lot is our cyanide ion, because it's stabilized by that triple bond to nitrogen. All right, likewise, we talked about last semester that we could deprotonate an alkyne, a terminal alkyne. You need a pretty strong base to do it, but it's doable. Okay, and there was another carbon nucleophile that we were just introduced to in our alcohols chapter as a way to make alcohols, where you create a new carbon-carbon bond. What did we do? What were those nucleophilic carbons? How do we make new carbon-carbon bonds, right, where our product is big and ugly on the other side? The Grignard, exactly. So Grignards are also carbon nucleophiles. And all of these here only work in basic conditions. You can't have a neutral carbon nucleophile. I mean, a Grignard's neutral, but that's in that really polar bond with magnesium. It's that weird organometallic compound. All right, but all of these are basic condition nucleophiles. And then what were our hydrogen nucleophiles? Also ways to create alcohols. So they share the same name. This is a hydride. This thing here is actually a terrible nucleophile. It's kind of surprising, but it's just a really good base. So rather than attaching itself to a carbon, it's always just going to pull off a hydrogen from somewhere. So this thing here is pretty much exclusively used for deprotonating alcohols. That's when you see those hydrides. That's what they're famous for. But we do have things that share that same name: lithium aluminum hydride and sodium borohydride. All right, if we looked at our mechanism, you would see that these have these negatively charged intermediates because they are basic nucleophiles. And nitrogen, I'm going to punt on for a little bit. We'll come back to that. All right, but here's our list of our aldehyde and ketone nucleophiles. Our neutral nucleophiles that we can use under acidic conditions, and our negatively charged or weird nucleophiles that we can use under basic conditions. Okay. So let's start practicing our basic conditions first, so it's a little bit easier. I just want you guys to take a second and complete this chemical equation for the following reactions. Based on what we discussed about our nucleophilic site, our electrophilic site, everybody take a second and draw me the product. All right, in this first one here, what is my electrophile? Electrophilic, carbonyl carbon, right? Where's my nucleophile here? Where's my nucleophilic site specifically? Carbon. So you're going to create a new bond between your nucleophile and your electrophile, right? That's the name of the game. What's your nucleophilic site? What's your electrophilic site? Create that new bond. Okay? And then our carbonyl oxygen is going to become what in our product? Where did this oxygen go here? What did it become? An alcohol. All right, so complete these chemical equations here. Count carbons. We'll talk, you do need a proton donor. We'll talk about what that would be here in a second. You don't have to do the mechanism, just draw me the final product there.
That's pretty short.
None of these are gem dials because there's not twin alcohol groups on it. So it would specifically be if we use water or hydroxide that would be a gem dial. No, they're right. But you do have your nucleophile attached to your electrophile in each of them, right? That's the common thread. Yeah. Count carbons. Okay, awesome. So I'm going to start by redrawing that electrophile, these 4 carbons here. Oops. Now I've got a new bond. What must live on the other side of that bond? It must be my nucleophile. And my nucleophile was that carbon of that cyanide ion, so I've got this triple bond. I'm being good and drawing it in this linear geometry, right? Because triple bonds are linear. And then what am I missing? I'm missing that formerly carbonyl oxygen becomes an alcohol group. Okay? Now, if we did our mechanism, we need something to protonate this oxygen. Exactly what you choose, kind of devil's in the details. But in an ideal world, what we like to use is the protonated version of whatever our nucleophile is. Okay? So if this is my nucleophile here, this alkoxide ion, what am I going to use as my solvent? What's going to be my proton donor here? Alcohol, specifically what? We know the name of this one. Ethanol. Right, so we would use an alkoxide ion in its matching ethanol solvent. All right, our nucleophile here is that oxygen. Our nucleophilic site is that oxygen. Our electrophilic site is that carbonyl carbon. So we're going to draw our, 2, 4, 6 carbons from our electrophile. And then when we make our new bond here, what must live on the other side? Must be that oxygen. Boom, boom. And then lastly, I'm missing on that same formerly carbonyl carbon. That formerly carbonyl oxygen is my alcohol group. Now with Grignards, you don't have that option. So in an ideal world, you use the protonated version of your nucleophile, or you have to follow it up with some second acidic workup step. So those are the two things that you'll see here. Just some way to provide a proton to that alkoxide ion. Here my nucleophile is that carbon in my Grignard. My electrophile is still that electrophilic carbonyl carbon. So we're going to start by redrawing those 3 carbons from our electrophile. This was my electrophilic site, so what must live on the other side? Must be that nucleophilic site. And then we have that alcohol. Boom. Okay, so in each case, I've attached my nucleophilic site to that electrophilic carbonyl carbon, creating that new bond, and then my carbonyl oxygen becomes an alcohol in my product. Cool? All right, so you're going to bear with me. We're going to title this next section acetyl formation, and then I'll explain to you in a second what an acetyl is. All right, this acetyl bond is particularly important in biochemistry because this is how sugars are linked to form starches. All right, so when we have too many calories, when we have too much sugar going on, our body takes that sugar and stores it for later by packaging it up into these starches. It links those sugar molecules together using what's called an acetyl bond. Okay, so how are we going to do this? So first of all, we're going to do, this occurs, and let's make note because this is really important. This is under acidic conditions. All right, so we're going to take, I'm going to zoom in here. Our ketone. I'm going to put it in acidic conditions. But in this case, instead of water being my nucleophile, I'm going to have this alcohol. All right, and given what we've discussed up until this point, I want everybody to try to predict what they think is going to happen here. I want the full mechanism here of this reaction. You'll have an extra bond here that you haven't broken.
That's what I'm saying.
There you go.
So then, let's use mine.
Snap it, pull it off, yeah.
There's nothing.
Well, you tell me, so if that's my nucleophile, what is my product going to be? Nice. On the right track. What's Gemini means twin? Yeah. Is it Latin or something? Okay.
There's nothing.
Just underneath. Yeah, awesome. Awesome. have one step missing because you haven't gotten rid of that hydrogen yet. Also put a plus sign on that oxygen.
Are you gonna get mad if I don't do the right arrows?
Yeah, of course.
How am I supposed to know when the reverse?
Oh, those arrows. No, I'm not gonna be mad at you for those arrows.
Oh, okay.
I don't care if you know whether it's reversible or not. Yep. So no, real quick. Where's this hydrogen is on that oxygen still? No, this one.
I was gonna move.
I didn't get like, got it.
Oh, okay.
I was
You got it.
saying to remove that.
You can use, yes, to remove that extra hydrogen, you're going to use something, it can be water or an alcohol. Yeah, one of those two. Okay. Cool, so as we've seen before, under these acidic conditions, in order to manage our charges, we got to first protonate that oxygen. Okay. Good question. I don't really care if you memorize which steps are reversible or not. I feel like we got enough on our plate. I am going to be good. I will note that all of our steps in this mechanism are reversible. Okay. So at this point here, whoops, I have a protonated ketone, making that carbonyl carbon an even better electrophile. And now when that pair of electrons gets bumped up onto that oxygen, it's going to be a neutral intermediate. Rather, that oxygen's neutral. I have a positive charge net. So then I have one more step. I wouldn't care if you used water, or what I think would probably be a little bit more correct, although I'm not going to be picky about it, would be an alcohol, since there's a lot of alcohol floating around in this solution. Either one of those, but importantly, it has to be a neutral base that you use. We can't have that strong base. All right. So what we form here, we have an alcohol attached to that carbonyl carbon and a hydroxyl group. Boom. So this is what's called a hemiacetal. But because we have these acidic conditions, this reaction does not stop here. So this is this intermediate that we form, but we're going to keep going here. We got more steps to get to our actual acetyl product. All right? So I'm going to tell you that not the very next intermediate, but the one after that looks like so. Whoa. Where now we have our carbon-oxygen double bond formed, but with that alcohol oxygen. So everybody take a second and try to predict, how did I get from my hemiacetal to this intermediate here? All right, what bonds do you need to form? What bonds do you need to break? Pay attention to your intermediates. Make sure they don't break the rules for acidic conditions. That's okay. Just make it ugly. You're going to study after class so much that you're going to redraw it again in your notebook and make it pretty. There's one missing intermediate here, so it would be the actual way to get there would be broken up into two steps. Not quite. No. Think about what bonds you're trying to break here. So you're breaking the wrong bonds.
So this step is wrong?
still have this R group attached. What I lost is that hydroxyl group.
I see what you mean.
I don't want you to make it epoxide.
Alright, well, I'm out of this.
So you could use like hydronium, but your arrows are going the wrong way because what's our electrophilic site in an acid?
You want me to make it
No, no, so in this acid here, it'd be your hydrogen. So the arrow should be pointing at your hydrogen. There you go. Yeah, wrong direction. And look, you can also always tell your arrows will never like point away from each other or at each other. They always flow in one direction. Electrons always flow in a particular direction. Okay, so I know everybody's very clever and they said, all right, well, I need to create a new carbon-oxygen bond and I need to break this carbon-oxygen bond. So let's just do that all in one step. 1, 2. All right, this would get you to this intermediate here. But why is that wrong? There's nothing illegal about my electron pushing arrows. Right? I didn't break any octet rules or anything like that. But what's wrong with this step here? Why wouldn't that be allowed? So A, you can think about it two ways. One, hydroxyl, bad leaving group. Hydroxide, bad leaving group. The other problem is, what's the problem mechanism-wise of kicking off a hydroxide ion under these acidic conditions? It's a strong base. We can't have that in our reaction scheme, right? We're not going to create any strong bases under acidic conditions. So how do we manage those charges?
We added hydrogen to the alcohol.
Yeah, we do a proton transfer step, right? So whenever we need to manage our charges, we use proton transfers. All right, so now in order to kick off this hydroxyl group, we're going to have to protonate it first. All right, now that it's got that extra bond and that positive charge, we can kick it off as a neutral water molecule. And that gets us to this intermediate here.
And then what? That's acetonitrite?
That's not, we're not done yet. Are we going to stop at this positively charged intermediate here? No, we got to keep going here. And you're going to help me complete this. I'm going to tell you in 2 more steps, we finally get to what we call an acetyl, which is when 2 alcohols have reacted with that carbonyl carbon. You're going to understand it so well that it's not going to be a memorization problem, right? You're just going to know the crap out of this. So it's just going to make so much sense. You don't have to worry about memorizing anything, all right? And this is our what we call an acetyl. Okay, so try to finish off this mechanism for me here. I'm going to tell you you're going to need a second molecule of your alcohol in order to do it. And so if we look, we have this carbonyl-ish compound here, right? Our carbon-oxygen double bond. So we can do our nucleophilic attack, and again, play that game where we kick that pair of electrons up onto that oxygen so that carbon doesn't have to break its its octet. And then we just have one more step to go here where this oxygen has this extra hydrogen. And we're going to deprotonating it using either water or an alcohol, I don't care which, to get to our acetyl. All right, so we have one round of our alcohol addition here forming our hemiacetal, but it doesn't stop there. We have yet another round of alcohol addition to form our acetyl. Okay, so let's just kind of summarize here. If we have, and we'll just use acetone as our example. If we react acetone with some alcohol under acidic conditions, and I know that, how do I know, if I just gave you this formula, how do you know it's acidic conditions? Because it's neutral. So this would be under acidic conditions. Again, you're not going to just get one round, but rather 2 rounds of nucleophilic attack, leading you to an acetyl. Okay, but if you took that same ketone or aldehyde and you reacted it with that same alcohol, but after deprotonating it, forming this alkoxide ion, then this would be not acidic conditions, but basic conditions. And how do I know it's basic? Because of the negative charge. Here you wouldn't get your full acetyl, but rather it would stop at that hemiacetal step. All right, and what you want to think about is that at acidic conditions, because you protonate that oxygen, it just makes that molecule an even better electrophile. So it can react with that nucleophile twice. All right, and let's say that we took this same sort of idea. I guess I'm going to label this here. This is a hemiacetal. But instead of using an alcohol, we swapped out this oxygen for a sulfur and used a thiol. All right, what we would see is this analogous reaction, where now we've formed sorry, those are R groups. Same idea, it reacts twice, forming what we call a a thioacetal. All right, again, 2 rounds of reaction. But if we did the same thing, but under basic conditions, so now we're not using a neutral thiol, but a thiolate ion. Again, we see under basic conditions just 1 round of nucleophilic attack, so we only add that sulfur once. All right, so to be clear, I'll try to color these here.
So they're still both called deacetals?
No, sorry. This is a hemithioacetal. Okay, so just to kind of color code here, under acidic conditions, that nucleophile is added twice. Under basic conditions, it's only added once. Same thing with our thiols. Under acidic conditions, added twice. Under basic conditions, added once. Cool. All right, so let's go back here. We're going to kind of kick this topic off of talking about nitrogen. Nitrogen we left off of our list. We said it was kind of special. All right. As we remember, under acidic conditions, we said what? No negative intermediates. Under basic conditions, no positive intermediates. But now we're going to introduce a third category here, what we call our neutral conditions. And under neutral conditions, all of those restrictions go away. Under neutral conditions, we can have both positive and negative intermediates. All right, and nitrogen is going to be our example of nucleophiles that will react under neutral conditions. So we could have ammonia, some primary amine, or a secondary amine. These will react with aldehydes and ketones under that new third category of being unneutral conditions. Okay? All right, so we're going to title this section imine with an I and enamine synthesis. And I'll explain what that means in a second. All right, importantly, what we're going to be using here are our nitrogen nucleophiles, which means that we have these neutral conditions. Neutral conditions here. All right, and what it meant to have neutral conditions, again, was that we could have both negative and positive intermediates are allowed. All right, I am going to note here that when we say neutral conditions, it's really like help for our mechanisms. But truthfully, if you carried out this reaction, it would have to be about pH 5 or 6. So you are under slightly acidic conditions. All right, meaning that we have some hydronium floating around. All right, so first of all, if I took an aldehyde or ketone, all right, and I should warn, this is going to be a long one too, so I'm going to do this all in a row here so that I can sort of map this out. All right. I'm going to take my ketone, and we're going to react it first with a primary amine. All right, I'm going to tell you that the very first step in this mechanism is actually nucleophilic attack. All right, and I want you to try to complete our mechanism here by filling in the remaining steps.
So real.
Did you just want one intermediate?
I was thinking of just the.
You could do it with one.
Love it. Yeah, all in one shot. Perfectly fine.
Why we can't tell these things.
No, I'm serious. You could break it up into two steps where you get like the solvent involved, but you can also just do it all in one shot. I'm perfectly okay with that.
Nice.
Okay, cool. All right, so if we just follow the intermediate here, we have this like right off the bat, we're breaking our rules for acidic and basic conditions, right? So this is why we need that new neutral conditions, because not only does our oxygen have a negative charge, but we have this nitrogen here that now has 4 bonds, so it has a positive charge. All right, and so where we're going here is we need to deprotonate our nitrogen and protonate our oxygen, right? Make everything neutral to create this. You can break this up into 2 steps, and in fact, that's how it is in our textbook. It's broken up into 2 steps involving the solvent, or you can just say this is a base, this is an acid. Let's just have this all in one shot. Boom, boom. All right. Do those 2 proton transfer steps in a row. All right, so this forms what we call a carbonyl amine. All right, but where we're going to pick up next time is it does not stop here. All right, this is our product that we would expect given all of our other nucleophilic addition reactions that we've seen. This is what we would expect to happen, is this carbonylamine. And what we're going to see is that it continues to go here until we finally form what we're going to call an imine, or not what we're going to call, but what the world calls an imine, and we'll pick up with that next class period. All right, but if you got to this carbonylamine, great. That's exactly where I would have expected you to be.
Is this still okay or should I not do
Yeah, so you can break it up into 2 steps involving the solvent, or you can just do the proton transfer all in 1 step. But this is fine.